So the goal today is to do some preparation for the modularity lifting patching argument. So let's start with a lemma. So let's recall that our coefficient field is always a finite extension of QL, and always being the range of integers and pi uniformizer and resonance field. I'll be talking about, for now, let's just sort of do some general theory that I'll start with a profinite group satisfying the finite condition that we talked about for existence of deformation ranges. In other words, how all the H1 and H2s are all finite. Like rho bar be a absolutely irreducible representation, and I want to assume that L does not by n. This way, I'll get a different unframed deformation rate. Okay, so I'll start with the first lemma. Maybe move it up. Discuss the relation between traces and coefficients in something. So lemma. So let A be this complete Noetherian local O algebra, and then rho is a lift of rho bar. It's continuous, and rho modulo maximal ideal is rho bar. And the first is so-called Schur's lemma for A coefficient. Says that if a scalar, or excuse me, if a matrix it conjugates rho to itself, then this matrix is just a scalar matrix. So the only thing that conjugates rho to itself is just a scalar matrix. The condition for this is that rho bar is absolutely irreducible, so that's important for this to be true. Secondly, it's called Carriol's lemma. It says the following, so that if B is a closed subring, and of course B is a complete Noetherian local O algebra, and it's a subring of this A. And suppose that I know that my trace of rho a priori is going to be going to lie in A, but then required to be in B. Then you can then supposedly we should imagine that somehow the rho should really have coefficient in B. In fact, that's what we kind of approve. That I can find a matrix A in PGLN of A such that A rho A inverse of gamma lands in GLN B. After conjugation, the image of this representation lands in B. So to prove these two. So first of all, I'm not going to say too much about it. This is essential induction on this matrix A modulo maximize u to the n power. And then you first do maximize u to square and maximize u to the cube and so on and so forth. So you can show that the corresponding A must be a scalar. Straightforward. So let's do the second one. The second one will take a little time to prove. So what we're going to do is I will inductively conjugate rho into, I guess, TL and of B plus the X more ideal NA. Okay? And then when taking a limit over N, I will eventually get the image into B. So now assume that we already done so for some N. With place of rho, however it be. I can just do some modification to this picture. So we may replace. Since the next step is I want to conjugate it into B plus maximum ideal A to the N plus first power. So I can might as well just modulo the first power, N plus first power. So I will replace A by B plus maximum ideal A and modulo maximum ideal A plus 1 power. And B by B intersect with this. Well, this is the same thing as saying B plus maximum ideal A and plus 1 modulo. Let's just say it. So after replacing these, we see that, I mean, like, I can definitely model out the point that we want to model out maximum ideal A to N plus first power. So after we've done that, then A modulo B, so B is still going to be a closed substance. So it's still going to be maybe it's sitting over here. See that this is still going to be closed inside of here. Then A mod B is now a finite dimensional F vector space. And of course A is just simply B plus maximum ideal A. So A is just tiny bit more than B. Then now, because it's a finite dimensional vector space, I can do it one dimension at a time. So now, by a further deduction, I may assume, in fact, that A mod B is just one dimensional by basically adding into between B and A. So each time you add one dimension into B, eventually until it becomes A. Or let's write it more explicitly. Let's just say that A is in fact B direct sum with another F. Where somehow this F epsilon is the thing you added into here. But then how does sort of A act on this epsilon? We know that the maximum ideal of A kills this epsilon. Because the thing you added on in epsilon belongs to here. So maximum ideal of A definitely kills it. Moreover, epsilon squared equals 0. Because, I mean, anything here is square 0. So, if that's the case, we can actually, we can further modulo maximum ideal B. Because maximum ideal of B is a subring, a subset of maximum ideal A, which also kills epsilon. And I can model out both of these by maximum ideal B, which will not affect our discussion. And thus, let's reduce it to the very sort of basic case that A being basically f of a joint epsilon modulo epsilon squared, is a very, very basic case. But even in this case, it's just going to take some time. So now this boils down to some calculation. Some explicit computation. So let's do that. So what do I have? Okay, so now we're basically essentially reducing to this situation. And what do I have? Okay, I have a representation rho. Let's write it down what it is. So I have a rho gamma. So that's going to be equal to, first of all, my rho lifts rho bar. So therefore, I guess if I read this elements in here as A plus B epsilon, then rho gamma. So the A and B will be somehow, the A must be just rho bar itself, and then plus some theta gamma for gamma. And then the goal is that I want to find some A such that after conjugating, and we know that the trace of theta gamma is 0 for any gamma. Okay? And I want to find an A in, well, rather I want to find a 1 plus epsilon A excuse me, and 1 plus matrix n f epsilon, such that after I conjugate my rho by this, so I guess 1 plus epsilon A rho bar gamma plus theta gamma epsilon 1 plus epsilon A minus 1. This belongs to just matrix. Okay. And let's write down what this explicitly means. So this is for any gamma. So this precisely means that so basically whatever term that contains epsilon should cancel out each other. So that would mean that I want my A minus, hold on, sorry. So I've got A, I've got some sort of rho, so I want some sort of A rho bar gamma minus rho bar gamma A. You have a plus theta gamma equals 0. Okay, so that's what I want. I want to find an A in the matrix such that A rho bar gamma minus rho bar gamma A plus theta gamma equals 0 for any gamma. Okay. So that's what we want to do. Let's do this. We need some more. Right. So we need some work to get this done. So the upshot is it's actually not that easy to prove this. So to do this, what we need to do is we actually want to extend this representation of rho bar, and this theta is not quite a representation, to the so-called group algebra. So I want to extend by linearity the induced map, the no map rho bar theta from the group algebra to the matrix. Okay. So group algebra means that it's just all the elements of the form, so A gamma gamma. Okay. Where A gamma belongs. Two things I want to do. So first of all, this rho bar is because rho bar itself, I mean, before getting to the group algebra, it's from gamma to GL n of f. excuse me, this is a group homomorphism. So therefore, when you pass it to the group algebra, this is a algebra homomorphism. And this is surjective because rho bar itself is absolutely irreducible. This is the I think it's called Artin-Wedeberger. Oh, I didn't write it down. So this is the Artin-Wedeberger. So I might have spelled it wrong. So it basically says that because rho bar as a representation is absolutely irreducible, then this is, as an algebraic map, this is actually surjective. The second thing is clear that from this, let's write it down. So I have for every pair gamma and delta in gamma. So rho is a homomorphism, so I get rho gamma delta. And that's fine, just write that. That's equal to rho gamma times rho delta. And rho gamma delta is rho bar gamma delta plus theta gamma delta epsilon. That's equal to rho bar gamma plus theta gamma epsilon. Rho bar delta plus theta delta epsilon. Right? Yeah? So now, I mean, basically the first, I guess rho bar, the rho bar is equal to, I guess these rho bars equal. So rho bar gamma delta is rho bar gamma times rho bar delta. But now I have to equality on the coefficient on epsilon. So I get theta of gamma delta is equal to rho bar gamma theta delta plus theta gamma rho bar delta. So I get something like that. Right. And thirdly, something we already know, that the choice of theta of gamma is 0. Okay, let's leave this for a bit, and let's move up here. So now we're gonna, essentially what we're gonna do is, we want to, next thing I want to understand is that somehow this gamma is a sort of infinite group, right? But I want to sort of, the real effect, how should I put this? So for example, if you want to understand the property of theta, because after I conjugation, right, I want the results of like sort of rho bar gamma to have something with the theta gamma. But the way that theta and the rho bar interact with each other is through the map rho bar in some sense. So therefore, instead of working with the group algebra F gamma, we just can simply work with this matrix algebra through this rho bar. So here's a claim. That's sort of in that spirit. So I have my F gamma. So I have the theta map here. So that's what the theta is. On the other hand, the group homomorphism says that gives a surjective map down by rho bar down to here. I want to say my theta really can be viewed as not just from this matrix, group algebra. It actually comes from this matrix algebra. You can find a unique theta, find a unique vectors as F theta. Okay. So that's what's going on. Of course, if factor, then it's unique because it's surjective. For every element here, its image here will be uniquely determined by something in here. So if it exists, then it's unique. So let's basically show, I need to show this actually exists. To do that, so it suffices to show that if I have something, if this sort of factors, I have to show that if something maps here to be 0, then if it factors, so it must be 0 here. And on the other hand, if I know the kernel row bar all maps to 0 here, then this map must factor through this map row bar. So basically, I need to show that kernel of row bar is actually contained in kernel of theta. So let's pick a delta in kernel of row bar. Oh, I forgot to say one thing here. Is that over here, especially these statements here, I guess I pointed out. So over here, I said, okay, I want an equality like so. Okay. So the equality works for, I guess, elements in gamma. But then by linearity, this actually holds for all gamma and delta in the group algebra by linearity. Because this is sort of, I guess, this equation is linear, it's sort of bilinear in gamma and delta. So now I want to take delta in kernel of row bar, but this is going to be some element in here. Okay. And also I forgot to say, over here, the same thing here. You said, okay, trace of theta gamma is equal to 0 for all the gamma in gamma, but also for all the gamma in F, the group algebra by linearity as well. So now I want to look at this expression, this expression we have over here. So let's see. So pick any delta in kernel of row bar. Then for any, I'm just going to use that expression here. So for any gamma in F, we take this expression here and take a choice of both sides. So let me sort of first of all copy this down. Choice of row bar gamma theta delta plus trace of theta gamma row bar of delta. Okay. So I copy that equation over here, and then I take trace of both sides. So now on the left hand side, so I pick a delta. For any gamma, I will have this equality. Now let's see what we have here. So choice of theta of something. So by the third property over there, this is always 0. Okay. Next, my delta belongs to the kernel of row bar. So okay, there we go. Row bar delta. So that's 0. So therefore, this entire term goes because row bar delta is 0. So now I have this choice of this thing being 0 because both of these are 0. But then what I'm saying is that this works for every gamma. As row bar gamma can be any matrix. Row bar gamma can be any matrix. So therefore, if theta delta pair with row bar gamma, if it always have trace 0 for any matrix row bar gamma, then this theta delta must be 0 itself. So we showed that if delta belongs to the kernel of row bar, then this delta, theta of this delta must be 0. Namely, the kernel of row bar is containing kernel theta, and therefore I have this relation here. Let's see, where do I want? Let's sort of set that. Okay. So now, so recall that what we want to do. So now I have the theta prime here. So let's rewrite. Let's see, what do I want? So now let's rewrite what we have here. So now we have some sort of theta prime from the matrix to the matrix. Okay. And remember that we know this, and we want to find an A such that this happens. Let's just say this happens. Right? But what is the theta here? The theta is, if you write that down, theta is theta prime of over rho prime. So theta of gamma, so factor through rho, first apply rho bar to gamma and then to theta. Right? So we want to find maybe I should do what we know first. Okay, anyway, we want to find what? I want to find some theta. I want to find A in the matrix such that A times, let me call this one delta, minus delta A plus theta prime of this delta equals to 0 for any delta in, well, maybe I should write x. Avoid delta. So we write x, for any x in the matrix. Right? That's what we want. But what do we know? What we know is somehow the first condition is already kind of used. That rho bar is surjective onto that. So basically, I have to translate second property and third property. So what does this property translate to? Oh well, first of all, know that theta prime is affilinear, of course. And the second property translates to that theta should be understood as theta prime of some sort of rho bar gamma delta. Okay? And rho bar gamma delta is the same thing as rho bar gamma, rho bar delta. So this condition really says that the theta prime, let's write xy for x for rho bar gamma and y for rho bar delta. So this would be theta xy equals to, so this is the x and this is theta prime y. And the other term is that y, theta first, so okay. Theta prime x, y. Okay? And then there's a trace condition. The trace condition basically says that the trace of every element is the trace of theta prime of any x equals 0. Any x. So essentially, now we're reducing to proving this implies this. Let's look at what we're doing here. So, what are these? So it seems that this trace of theta prime of x equals 0 means that there's another way to think of this: is theta x belongs to SLN. The trace 0, the algebra of this. Okay. On the other hand, this property, the second property means that theta prime is a derivative in SLN. Well, matrix. I mean, essentially because the image lands in SLN, so I can just consider those x in SLN. And what I want is that I want to show that theta, essentially I want to show basically theta prime, so we write this, theta of x equals to x bracket A. So theta prime is given by the bracket. So this is, I think this is, at least over C, this is a classical statement, that every derivative of SLN is given by B bracket. Or rather, this is how this works for all the semi-simple Lie algebras. But we are in calculus P, there's some little work to be done. So let me leave this as an exercise for you. show that for SLN, at least when P does not divide n, excuse me, L does not divide n, coefficient L does not divide n, somehow all the derivatives are given by Lie brackets. Okay, so this finished the proof of this lemma, which says somehow it says that the choice determines, I guess, where the representation, the image of the basic representation of this representation after conjugation. So here's a corollary. Of this lemma. This is where we want to get at. So it says this is universal. Information ring R rho bar is topologically generated over O by elements twice of rho universal of gamma. Of course, if you take trace, it definitely belongs to rho bar for gamma in a dense subset. Gamma 0. So what I have in mind is that gamma is a Galois group of a global field, and gamma 0 are the set of Frobenius elements. So therefore, they're dense in here. I'm taking the Frobenius trace. So this will show the statement we didn't prove last time, that the unfirm differential ring is generated by the trace of Frobenius. Or equivalently, I'm just rewriting what we have here. Excuse me. I take the sort of formal power series in the variables given by this gamma naught. This will surject onto R rho bar if I send my T gamma to the choice of rho universal gamma. But not quite, not finished yet. But somehow, because this T gamma over here will be topologically nilpotent, so I want to send that to something over here to be topologically nilpotent. Very likely, the trace of this will be a unit. So therefore, what I should have done is a minus trace of rho gamma. Take any lift. To O. So I take the choice of the universal one minus any lift. So this will be circular. So proof. So let R rho bar prime denote the image of this map. Let me call it psi. Okay. So suppose this is not surjective. So then we can show that it's actually a closed subring of this one by some topological argument by a Bob lemma. We can conjugate it. By a Bob lemma, you see that if you know the sort of the choice, I mean, you already know that the choice of rho belongs to the image of belongs to this. So this is R rho bar prime. This is inside R rho bar. The choice of rho, at least for dense subset, the image lands in here. But because it's dense, and we can show actually this is closed by some sort of topological argument, that the trace of any element in gamma belongs here. So therefore, by the lemma above, we can conjugate this rho universal so that this rho universal actually takes image in this, well, hypothetically smaller ring. Now, we're almost done. Now, by the universal property of deformation ring, then I get remember that I have a natural inclusion this way, but then the universal property, because I have a representation with coefficient in smaller one, which lifts rho bar, so therefore I get them that's going this way. So this will imply that's our rho bar. Essentially. By that way. Okay. So that's roughly speaking it's some sort of wrap up from last time that would show that some remaining things from last time that we showed that the unfirm deformation ring is generated or it's topologically generated by the trace of Robinian. For the remaining time today, we want to talk about or give a brief introduction discussion of the new forms / O form theory. And gamma naught versus gamma 1 theory. So let's see what I want to do. So here's what we're going to do in terms of patching argument. So I will be assuming entry at least 4 to avoid some so that things are neat, so-called. And I want to take QA prime and Q is not by n. So for patching, in some sense, we'll always kind of start with the very bottom here. From x gamma, I can do gamma 1 or gamma 0 here, doesn't really matter. I feel like I don't have enough space, maybe I'll just move to the other side. So the picture we want to do is I want to start out with some x1 gamma. x1, excuse me, gamma 1n. But sometimes I like to, in applications to Fermat's theorem, it's enough to start with gamma naught n. But soon, when we rise up to levels, I may have to sort of use. But eventually, when we add some levels, we'll do gamma 1 levels. So I can rise up. This intersect is gamma naught q. And so we'll go up to this level, gamma 1 star q I discussed last time. So let's recall the definition of these again. So my q is going to be converge to 1 modulo L. In fact, I want to take L to the R, precisely divide L to -1. And recall from last time that gamma naught q is all the A, B, C, D, SL to Z, such that Q divides C. And and what I want is Q divide C and then Q divide A minus 1 and D minus 1. Because it determines 1, so F1 divides in there. Okay. But in between, I want to find a gamma 1 star Q in between, so that this degree here is L to the R. So I want this so that this difference is L to the R. Okay, so this is all the A, B, C, D. So last time I made a mistake, I think. It's gamma naught Q. Then the relation I want is that A modulo D. So last time I wrote P to the R is congruent to 1 mod. Mod Q. Excuse me, mod Q, right? In fact, it should be Q minus 1 modulo L to the R. So that the difference here is L to the R, and then the difference here is Q minus 1 to the L to the R here. Okay. Basically, what I'm saying is that this quotient here will have Q minus 1 over L to the R solutions. So therefore, making this degree Q minus 1 over L to the R, and therefore this degree is L to the R. Like that. Right. And what are the corresponding maps? So I'll be for application to patching argument. This is how I'm going to be considering. And what are the corresponding maps? Well, let's start with the bottom one. So I'll have a CE and a curve, and an n torsion point, and a subgroup of order Q. The two projections is given by E of Pn. Writing this way, E quotient out by the order Q subgroup, and then Pn plus PQ subgroup, and then PQ. Okay. And then coming down this way, it's basically the same. Basically refines what we know about the Q portion. So this is some sort of PQ. It's some subgroup generated by PQ. So it's not precisely an element of order P, but sort of an order P up to, I guess, some ambiguity here. Specific. It's something. So you can define some level like that. And for the modularity lifting techniques, what we're going to do is going the other way. Is to talk about space of modular forms, or in fact, sort of, I should have said dual of that. But for the moment, let's talk about this modular form level. I have space of modular forms here. I can take projections up or back here towards project to get something here. So I'll discuss this in step 1 very soon. And then the next step is to understand how this goes up to here. Step 2. Okay. So discuss this. So the process of patching is that we're going to kind of start at bottom and then pull it back to this way and do some. I'll explain what kind of game we have to do, and then pull it back. So let's first of all discuss step 1. Right. So let's step 1. Let's do the so-called classical theory first. This is a classical old form, new form theory. In the case we consider here, this is also called Q stabilization. Or in fact, it's often used in the context when Q is P. It's usually called P stabilization. That's how my prime now is Q, so Q stabilization. So it's the following, as which kind of is discussed over there. So I have I'm just pulling back. There are two ways to pull back this to what you have upstairs. So maybe a better way. Well, let's write down what it is. So I have two ways to pull it back. Let's see. So maybe it's better to do it this way. Well, let's do it this way first. We'll hesitate on what to do. So let me just write, there are two maps. Okay. So the two maps are a little bit different. Right. So the first one is V. Other one is FQ. Okay. So I have two projection pullbacks. So what we have here is that over here I have the so-called Heck operator at Q, because now Q does not divide in, as we discussed, as we assumed. Therefore, the Heck operator acts on this one. But on the other hand, there's another Heck operator at Q acts on this one, but now Q divides a level. So this Heck operator is usually denoted by UQ as opposed to TQ. So these two are both Heck operators at Q, but somehow they have different expressions on Q expression. Oh, sorry. This Q agrees with the Q and Q expressions, but I think there shouldn't be any problem understanding of what's going on. Okay? So if F is a TQ eigen form with eigenvalue AQ and also at the same time an eigenform for all diamond operators. I.e., you can find a chi, a so-called Newton-Typus character, such that if you diamond D of F of Z, that pi D F. Suppose your F is like so. Now I want to understand how this F would generate some subspace on the right hand side when the level, there is a governor level. But see, you have two ways to use, starting with one F, you somehow create two different F. One is just F as itself, the other one is F cubed. Those two forms are different. So let alpha and beta be two roots of x squared minus aq x plus q to the k minus 1 iq plus 0. So let's assume that alpha is different from beta. So it's a conjecture that this is always true. I should be careful here. So it's conjecturally true that this held for modular forms, but not for any sort of naive generalizations of this. For example, Huron form, this will not. So alpha is possibly equal to beta. But for modular form, it's conjectural that alpha is always not equal to beta. Okay. So suppose I have two zeros, this quadratic equation I can solve for two zeros. Then I can set f alpha of z to the f z minus beta f q z. And then call it f beta z to the f z minus alpha times f q z. It turns out starting from f, a TQ eigenform, and of course being an eigenform with diamond operators, if you write things like so, these are both UQ eigenforms with eigenvalues alpha and beta respectively. So this has eigenvalue alpha, this has eigenvalue beta. Maybe let's check this. Let's check this. In fact, I'm going to exactly check this, but let's check this is true. Let's first of all do UQ of FQZ. Okay. So what is FQZ? You apply UQ to this expression as sum of A and Qn. As I said, somehow Q is a prime and this Q is a Q expansion. Let's just pretend that's not true. Okay. And the formula for UQ is that I guess so. This is really the coefficient with Qn power of Q. Terrible. Anyway, so when you do UQ to that, you just get back it. You just get this, and it's precise of F. It says that you didn't do anything. Well, so therefore UQ of FQZ gives you FC. On the other hand, if you do it on FC, this is, of course, we know the formula. This is AQN, Q to the N. But then I want to relate to what F is, or like TQX of F. So this is nothing but just TQ of FC minus Q to the K minus 1 pi Q times the other part of in the expression of TQ, which is sort of A and QQN. Right? Remember that TQ acting on the modular form F has two parts. One is this part, and the other part is this part. But we point out that what we have here, this is just simply F of QZ. Okay. So, conclusion. The conclusion is that the conclusion is that if I consider this on basis, if I consider the basis of this UQ action on the given basis FZ and FQZ, this is given by well, UQ action on FC gives you TQ of F minus that thing, so you get TQ minus Q K minus 1 pi Q. Whereas UQX on the other term, you get to FZ. You get 1 and 0. Okay? So if your F were a TQ eigenform, this TQ should be replaced by AQ. And this alpha and beta are precisely the eigenvalue of this 2x2 matrix. And the way you write down FZ minus beta, FQZ and FZ minus alpha FQZ are precisely the eigenvectors of this matrix. So that's what it is. So let's make it again. So this process of turning TQ eigenforms into UQ eigenforms is called Q stabilization. This is important, I guess, very important in p-adic number theory. P-adic theory of modular forms. Right. Anyways. So that's what sort of we can do, starting from one F here. I create somehow essentially two F's here. So in fact, this is sort of new form theory. says the following, that in fact, if I take two copies of this, one using project 1, the other using projection 2, pulse back to sk of gamma 1 and intersect with this. By sending f z, if I have a pair f comma z, which is g, I send it to f z, say plus or minus doesn't matter, g t z. Okay. So this is injective. Moreover, there's a natural complementary space. Complement space. So somehow there's a natural subspace in this one. I'm going to call it sk of gamma naught 1 and intersect with gamma naught q. Q mu space. Such that, because it's injective, so this direct sum with this is equal to the entire space. Okay, let me say a little bit more about this natural subspace here. There are two ways to see where this natural subspace. There are two ways to see this natural subspace. They're sort of the same thing. There are two ways to say this. Let's see. So either I can define, so either this complement space is defined as the orthogonal complement to the orthogonal complement to the image for the so-called Peterson inner product. Inner product. So maybe like on the space of modular forms, for example, on sk gamma 1 n intersect with gamma naught q, there exists a natural Hermitian form, or sort of non-degenerate Hermitian form, by sending to the integration on the modular curve, where we use this half line, proportional by gamma 1 n intersect with gamma naught q. In this case, fz, g bar z. I don't remember this. Should be something like k minus 2. Y k minus 2. Oh, it could be something like this. I could be wrong. Or maybe better way to write this. I could be wrong here. I didn't prepare for this. So. Okay. So you have some sort of natural non-degenerate Hermitian form on this one. You have space mapping into this, and you can take an orthogonal complement. That's so-called Q space. Or in a fancy way, you can say that this sk. Let's rewrite this. If you consider eigenspace decomposition, or maybe eigenspace decomposition by Hankel papers, TL prime for L prime not dividing N on Q. Meaning that this space here can be really written as the direct sum of whatever is the image you have over here. Let's say sk of gamma naught n, c direct sum twice. We call it q odd. So that's just sk direct sum with sk of gamma 1n to nu here. And somehow this decomposition is sort of respect all the Heck actions. Namely, each of the direct summand is a Heck equivariant, Heck stable under the Heck operator away from n and q. And there's a unique such space which is Heck stable under Heck stable, and which is a complement of the space here. Okay, and the QO space is essentially what we have here, sk gamma 1n, and the other space has a property which I won't have time to prove, but you can. It's not that difficult to prove that. This entire thing has a UQ action. We kind of discussed the UQ action over here by the Q stabilization process over there. But the Q action over here, one can show that the Q action here definitely satisfies the simple property that UQ squared must be equal to Q to the K minus 2 times chi Q. This is K minus 2, not K minus 1. Okay? So therefore, the eigenvalue of UQ on this space should be square root of this one, plus or minus. Okay. So this is what's happening in some sort of step 1 here. And when we go from this space to this space. But now, we really need the story overall. So that's what we're doing. So let's recast the story. So now as before, let's fix the rho bar in absolute for the Galois group of Q goes to GR to F. This is absolutely reducible. And the determinant of rho bar is chi cyclotomic. I think it should be 1 minus k times chi. So I made a mistake somehow in associated Galois group. It should be 1 minus k chi. And here this chi is a Galois group of QS going to Galois group of Q. It's some sort of finite, it depends on the Nibben-Typus character. This comes something with the Nibben-Typus. Remember, the Nibben-Typus has a character from Z mod and Z cross to F. And then that can be identified with the cyclotomic extension, where somehow like chi, sort of composition of the system all that. And let Q be a prime. Q does not divide n. So my Q is congruent to 1 modulo L. And assume that rho bar for Venus Q has distinct eigenvalues. Alpha bar, beta bar in F cross. And then I'll lift them to alpha, beta, all arbitrarily. This is not important, but I just, when I define it, it makes the writing a little bit easier. but one thing I want to note is that given all these data, because my determinant rho bar is equal to this chi times cyclotomic 1 minus k, so therefore you know that this alpha bar times beta bar is chi q times q to the I think k minus 1, because my q is congruent to 1 mod L. So therefore, it's congruent to chi q. Now I want to discuss some sort of maximal ideal of the Hecke operator. I'm going to call it M rho bar to be the ideal in the Hecke algebra for modular forms with level gamma 1n. It's generated by uniformizer TQ prime minus trace rho bar for B is Q prime Q for all Q prime not dividing NQ. So I want to point out that a small I want to say that this is whatever I have here, this is the same thing as MQ and rho bar, adding this TQ minus tracer for Venus Q inside of this. In the sense that this TQ minus tracer for Venus Q to Q, also could be rho bar for Venus Q. It's already contained in the maximal ideal. The reason is by Schermerhorn density that somehow this tracer, this Frobenius element of Q is can be approximated by other Frobenius elements, and therefore their traces will be, or the actions of this, the information is already contained in under Q prime. So this is in the sense that I don't need to consider Hecke operator at Q. I can remove that from it. And now I want to do similar things. This is ideal in H, let me call it gamma 1 and intersect with gamma naught Q. This is again generated by the same, generated by the same thing. Now I want to recast the story here. More or less leave it in. Then I can write this localized M rho bar. Remember that on this one, TQ minus alpha beta alpha plus gamma x nilpotent. Because TQ is supposed to, in terms of x by trace of rho bar from Venus, and then somehow the difference must be kind of divisible by L, and then therefore this plus x, at least, topologically nilpotent. And this pulls back via two maps. Let's see. Two maps. You can pulse back too. Why look like the same thing? But this space here is a direct sum of the O space. QO space and Q mu space. I claim that it's sort of the same thing as SK. Just look at the QO space. Why is that? That's because over the SK, it's a long word. Q mu space. The UQ will be a UQ square x by, or maybe just write the UQ x by plus minus square root of chi q x because UQ here, square x by some q to the power, but q is coming 1 mod L, so it's just chi q. And plus minus square root of chi q. But this is never equal to alpha bar or beta bar. Because we discussed over here that alpha bar is different from our beta bar. And the product is chi q. So therefore, I guess square root chi q can't not be equal to alpha bar. If that's equal to alpha bar, then beta bar will be the same thing. Right. So in other words, because it's space here, this rho q is x by the wrong thing. So therefore, corresponding to other tq prime can't act in the same way as indicated by rho bar. So somehow, like the new part, UQ action it's a wrong action. So therefore, going down from here, I just only see the O part. And then because alpha is not equal to beta, so this O part, in fact, is isomorphic to the two new part, to the two portion. So this M rho bar, call it alpha, right? Alpha bar. So this is given by this maximal ideal and rho bar prime, together with the operator UQ minus alpha, and this direct sum is SK of gamma 1n intersect with gamma naught Q and rho bar prime beta. Okay, this beta is given by rho Q minus beta. So somehow the idea is that this space maps into, there are two ways to pull it back to here, and one goes in here and one goes in here. So the lemma is that indeed any copy of this will be isomorphic to the original one. Fix alpha bar, then we have the isomorphism. That SK going on n O and rho bar under prediction 1 pull back minus beta prediction 2 pull back. This goes to SK of gamma 0 n, which is gamma 1, gamma naught Q, O, and rho bar prime, comma alpha. This is nice. And moreover, over here, S rho bar S x up here, and over here, the same thing, the same. Yeah, the same thing here. Oh, well, maybe I should say this is beta 2 down here. Let's explain what beta 2 is. Where beta 2 is a unique root of x squared minus pq x plus q to the k minus 1 q in the Heck algebra for this level, which reduces to beta bar. So such thing exists by Hessel's law. this is a unique root in here. I think it was H1. Because I have a T here. So this is H1. So there's a unique solution here. So summary of what we kind of see here is that we may see the same row bar component. And after choosing a root, you can either choose row alpha or beta. Well, it doesn't matter. I can run bar because I have bar instead. After choosing between alpha and beta, I can see the same row bar component of modular forms in SK, gamma 1 and intersect with gamma naught Q. So let's put this back. The picture we have over here, which is that somehow the precise story in step 1 we just completed is that if you localize this as some m row bar here, then over here you just localize it as some m row bar alpha. And there will be a map on the back saying that these are isomorphic to each other. So this is the first step here. And next I'll explain the second step, which is more complicated. Well, it is which is a little bit different flavor. Not more complicated. Step 2. So say I know that L to the M exactly divides P minus 1, Q minus 1. I already defined, I already kind of erased, so let me just kind of recall. Sort of recall that my gamma 1 star Q is all the A, B, C, D, where gamma naught Q, such that A mod D of Q minus 1 spoken by L to the M equals coming to 1 mod Q. Okay? Also, somehow it's important to require the ratio to satisfy some sort of property. So, as opposed to requiring the element D to satisfy some property. In that sense, somehow, I guess this is not very accurate. So we have to modify slightly what this means, but anyhow, not so important. And now let's maybe for simplicity, let's see, what do I want? Okay, that's fine. Let's look at. Okay, so what we have here is that I have my modular curve. Mapping y with pi q. And this is some sort of quotient by z mod L to the mz. Mapping that down to x gamma 1. Remember that this sitting inside, this group sitting inside gamma naught q has index L to the M. Okay? So if I have a quotient this way, then I have, so this maps here, so this maps back. Okay, so you have this, and then definitely you can pull back the space of modular forms. So over here, let's pull back. First, pull back the modular form. then I localize the same thing. M rho bar alpha. Let me double prime because it's going to be a different level. This is M rho bar alpha prime. Okay? So that's that. So this is pi q upper star. The next is that somehow for the patching argument, it's actually more convenient to talk about the dual of this space. This is not very serious issue. So this dual means half of this thing over O. These are let me say O for these are finite free O modules. Half over O will be scaled finite free O modules. But for functionality, it's better to go this way. That's sort of this is sort of consistent with the sorry, I'm a little confused. So hold on a second. Right. My bad. So this curve maps down to that. The function's cohomology, pulling back function from here to here. Right. Okay. That's good. But math going this way. My bad. Okay. So let's see how the Galois move action. So this will carry an action of R rho bar as before. R rho bar, which is crystalline, and level 0 k minus 1. Over here, I would have the same thing, but then now I have to put a Q here. I'll explain what the Q means in a bit. So this is level 0 k minus 1. K Q means to allow ramification at Q. And because it allows ramification at Q, so this is a bigger ring than the other one. So correspondingly, a surjective map. And this diagram is in the sense that if you have an element here with this Galois action, the map over here will be corresponding to this action. So now let's look a little bit in more detail of the difference between the deformation rings. And I needed that to be compatible with something we see in automorphic theory. So this is actually very important in the patching argument. So recall Q. So the rho bar Q. So I'll go to QQ to GL to F. I'm going to send the Frobenius at Q to alpha bar and beta bar. And my type or ellipse determine rho bar Q to an unramified ellipse this thing here. And it's unramified at Q. Let's talk about the frame deformation ring. That will give us some clue of what's going on here. The universal frame deformation ring of this I left this as an exercise for you to work on in one of the problem sets. So it turns out this is deformation ring is precisely x, y, s, and z. Or this is one subject to this relation here, where the universal difference and the frame deformation is the following. It's a rho Q representing phi q for the matrix 1x, 1x, y1, alpha plus s, chi of phi q, quotient by alpha plus s, 1y, x. So basically there are some two eigenvectors, 1y and x1. And then the forbiddance will be acting by these two. And correspondingly, tau q will be acting by, sort of in the same way on, so they also have some sort of two eigenvectors. Where the eigenvalues here are 1 plus z and 1 over 1 plus z. And then 1 plus z is L to the m roots of unity. So this is different. This is different from what's the verse about the situation here. The time verification can be so you can have some sort of time verification on the diagonal terms. And if you only allow unratified information, quotient by z, basically you kill the z here, so this becomes the identity matrix, and then these two clashes. So tau will act further. So this is what's happened for the framed local deformation ring. Unfortunately, you cannot talk about unframed deformation ring because, I mean, this is not irreducible. But nonetheless, somehow the similar argument can work in the unframed situation there, where you can sort of talk about eigenvectors and so on and so forth. So that's what we're going to do. So now switch to the global deformation ring, R rho bar. With this additional verification allowed at Q, this rho universal of phi q has a unique eigenvector V alpha such that the eigenvalue comes with alpha bar modulo the max one 0. Maybe I should point out that I often say, okay, there is a unique eigenvector. So, but this is not done in the fraction field or something. You actually explicitly write down. It's starting with a vector saying 1, 0, and then you lift it all the way up using Hessel knowledge. Not like you're like sort of solving it. Not like solving the fraction field or something. And then this V alpha should be thought of as somehow this vector 1y or something. Right? I think it was just 1y here, which corresponds to this eigenvector. And then let z to be the eigenvalue of rho universal of tau q on V alpha. Oh, I should say that tau q is the time generator for this thing. Tau q is the time generator for the calculus for q. And similar to the local calculation, you can show that I guess there's also an eigenvector which is sort of V of sort of this also eigenvector looks like x1, which has this eigenvalue, and somehow tau q actually must be sort of diagonal with respect to these two vectors. And you can consider z to be this eigenvalue minus 1. And then, just like in the local situation, that this entire thing is an OZ modulo this thing algebra. So in the same way, the global one, Q, trace of 0, comma k minus 1, is an OZ modulo z minus z plus 1 to the L to the m minus 1 algebra. Maybe I should point out that this quotient is precisely the group algebra for z mod L to the mz. And basically this is where it comes from. That's how you see z plus 1 is Z plus y can be solved as 1. And moreover, that if you remove the if you want to sort of get rid of the ramification at Q, this is simply R rho bar Q, original one. Right. So that's what we're doing on the step 2 over there. So over here, maybe I should say before that I have some dual here, and this is somehow inserted in that we'll see later on, and this we localize M rho bar R prime. It's prime and double prime. Let's see if I have enough space here. I can stick this thing in here. I'm going to draw a diagonal very similar to that diagonal over there. It's actually copying that over. So now, I said, let's say moreover, we know that when we associate Galois rotations, the diagonal operator corresponds to the time inertia actor. So the compatibility of diagonal operator and inertia group action implies that, so let's have that diagonal over there as K of gamma 1 and intersect with gamma. Oh shoot, I loaded wrong. Very confused by this, sorry. So just start Q here. 0 here, my bad. Sorry. This one was the level. Very confused. So I have this thing, dual. And rho bar R SK. So okay, so then this is part of double prime. Part of double prime. And recall that we have, we're just copying what I have everything. So, it's R rho bar crystalline. Q. This X here. And over here, because we just proved that this is a O of Z mod L to the MZ algebra. And over here, this is just O. This is specific quotient by Z. This is quotient by Z. So this is a Cartesian, and this is also kind of somehow. Also, this X on here, this is also Cartesian. So that, together with that, actually. So okay, at least the ring level, somehow we have this sort of usual diagram. So, namely, so what this diagram entails is that this thing, on the one hand, it maps over here. There, what this diagram entails. It says that somehow this thing maps over here, really sends the generator here to the time, sort of time element action, the tau here. Whereas on the other hand, this one axon here, this is through diamond operator. That Z mod L to the MZ, first mapping into Z mod QZ cross. Remember that this is sort of L torsion part of this thing. And then this one will act on the space of sk. So in other words, inertial element action is the same thing as diagonal operator action. Finally, punchline. Important fact. The final important fact we're going to use next time is that sk emerald bar prime. This is in fact a free OZ mod of the MD mod Q. And if I cancel this with the augmentation quotient by the augmentation idea, anyway, if I cancel this free module with the augmentation idea, just kill all the group actions. So this is the isomorphic thing. And apply step 1. It's the same thing as gamma 1. So in other words, what we effectively did is that I started out with this module and made something which is faster than this one. By first of all going up to gamma naught q and picking a piece inside of that, so this is your isomorphic. And then you kind of grow into something a little bit larger, where when you quotient out by the augmentation idea, I get that. At the same time, considering the Galois side, I start out with the original deformation ring. I get to move up a little bit to something a little bit bigger, which is this sort of crystalline deformation. Which is this deformation where I allow ramification at Q. And the two grow are compatible in the sense that the diagonal operator on this space is the same thing as the tiny inertial action in the deformation space, so to speak. So this whole commutation diagram. So I'll stop here, and the next time we'll continue to move. I'll get even closer to the patch curve.